Good morning. This is the 14.5 video. We are moving from double integrals to triple integrals. And just like before, when we started with double integrals over rectangles here, they kind of ease you into it. But these are not just rectangles. This is rectangular coordinates. And so in rectangular coordinates, that just means X, Y, and Z. Because later in 14.7, we're going to do triple integrals with cylindrical coordinates and spherical coordinates. So cylindrical coordinates, that's just going to be polar in 3D. And so this is the X, Y, and Z stuff in this section, and then we'll get into the not rectangular coordinates later. So it gives you a little introduction. This is page 786, a little introduction here about what triple integrals are going to do, and we're going to see a lot more of this in chapter 15, which is our next chapter. So really important that you get the hang of this. So they start with a simple one here. If you remember from earlier in chapter 14, a double integral of a function is volume. A double integral of 1 was area. So a triple integral of 1 is volume. And so notice here the function is 1. Now a couple things are different. They're using D instead of R because the D is now 3-dimensional. The R is 2-dimensional. And then they're using dV instead of dA because dA was dx dy or dy dx. dV, there's actually 6 possible combinations. dz, dx, dy, dz, dy, dx, blah, blah, blah. I'm not going to go through all 6 of them right this minute, but there's 6 possible combinations for the dV now. So at the bottom of the page, they talk about how to find the limits of integration. This would be if you were going to do z, y, and then x. So I'll let you read this on your own. It's obviously always starting with sketch the region. And then next would be find the z, then the y, then the x. That's here. The setup for if you have z first, then y, then x. So notice the outermost one's numbers, and then the inner ones are functions. So the middle one is a function of a single variable, the innermost one a function of 2 variables. So it gets less dimensions as you go out. So it's a function of 2 variables, a function of 1 variable, and a constant as you move yourself out. All right, and then they have at the bottom of page 791, average value. This would be now for a function of 3 variables. So this f would be f of x, y, z. So you're finding the volume of D. So the average value before was 1 over the area. Now it's 1 over the volume, but it's a similar kind of problem. All right, so let's look at the formulas here in my notes. Again, we have volume is the triple integral when you're integrating 1. So there's a 1 there. This is the formula that we saw for volume before. A double integral of a function is volume, or a triple integral of 1 is volume. Just like with area, we could do it with a double integral of 1 or a single integral of a function. So area had the 2 different ways to do it. Volume has the 2 different ways to do it. It's the same kind of principle. So this is, again, one of 6 possible orders. This is the one that was in your book. Again, notice you have a function of 3 variables here. You have 2 variables, 1 variable, no variables. And then the average value formula. So that's our formulas. Here I wrote all the possible combinations. Just again a reminder, R is a 2-dimensional region, D is a 3-dimensional region, dA, which is what you have for double integrals, could only have 2 possible orders, dx dy or dy dx. But dV, here's all the 6 possible combinations of the orders. And so depending on what you're given is which one's easier. So just like in double integrals, this was kind of my default one just because it works out nicely that y is a function of x. Kind of the default one on this one would be this last one here. Z makes sense to be a function of x and y. Y, it makes sense to be a function of x. And so when they're all equally easy, then this is kind of the default one. But depending on what you're given, some are easier than others. And so we'll look at some different orders on how to set those up. But now we're going to look at some examples. So page 792, we're going to look here at triple integrals. They're having you set them up all 6 ways. In general, you would not do this. In general, you would just set it up one way. But here, just for practice, they're having you set it up all 6 ways. So you've got, you're in the first octant, you've got the cylinder, and you've got the plane. So I tried to draw it. I didn't draw it just in the first octant because that was kind of hard for me to do. But I drew this. Here's the cylinder. It's opening around the y-axis because the y is missing. Here's the plane. Sorry, it looks kind of bad. You can see all my white out. I am not an artist. I am a mathematician. So that plane is leaning a little more than it should. It should be kind of straight up and down, but whatever. So just imagine like a paper towel roll, you know, the cardboard thing inside the paper towel. So imagine that cardboard thing inside the paper towels, that roll, and then a piece of paper that's vertical. And that's kind of what's going on here. That's your two shapes. Okay. So again, but it's only in the first octant. So in the first octant, you know, you're cutting off the back side and the bottom side and the left side, and you just have it in the first octant. So it would be kind of, let me see if I can draw it. What looks like that? Whoops, that should be dotted. I don't know what looks like that, but something kind of like that. Like, I know what looks like that. Okay, so you know if you have air conditioning vents in your floor or ceiling, I don't know where you would use these things, but they have those little plastic things that stick to it with magnets to force the air to go in a certain direction. That's what that looks like. That's exactly what that is. Okay, so that's what it would look like just in the first octant. Okay, so, oh, I did draw it. My stinking bunch of goodness. Whatever. Here it is. I did draw it. I thought I didn't. Okay, so you have, what you want to do is group them together in 3 groups, and it's based on which one you're doing first. So this would be if I was doing X first. Okay, so if I'm going to do X first, I can do X first and then Y and Z, or then Z and Y. But why you want to do it in these groups like this with the X first is because then you look at your 3-dimensional picture for whichever one you're doing first, and you see which way that variable goes. So X goes back to front. And so when you're setting this up, you say, okay, what's in the back of my region? And so if you look at this, that flat part in the back, that would be the YZ plane. That's where X is 0. And then in the front of the region, as you come forward, then you're hitting that cylinder, right? So in the front is the cylinder. So you need the equation for the cylinder, but you need it solved for X. So I'm going to solve it for X. I had originally the plus or minus, but because I'm in the first octant, X is positive, so it's just this. Okay, so in the 3-dimensional region, whatever variable you're doing first, that's what you're looking at it in terms of 3D. Okay, so in the 3-dimensional region, if I'm looking at X first, X goes from the back to the front. So in the back is the YZ plane. It's the YZ plane. Then you come forward and you hit the cylinder. So X is between the YZ plane, which is 0, and the cylinder, which is this. And then if you look at the projection, now if you've done X first, then the 2-dimensional projection is in the leftover variables plane. So it would be the YZ plane. So you're looking at the projection of that in the YZ plane. So if you look at your 3-dimensional picture, the YZ plane, that would be the back. See how that's just a rectangle? So here's the projection in the YZ plane. And since it's just a rectangle, then you have Y and Z both being between numbers. And so you can do Y first or you can do Z first. And I guess it's on the next page. Hold on. Yeah. So here would be your 2 integrals. Okay, so notice here's X, then Y, then Z, and here's X, then Z, then Y. All right, so let's look at the next group. We're going to do Y first now. So these are the 2 with Y first. So let's go back over here to my picture. When you look at the first one, you're looking at the 3-dimensional region. So Y moves left to right. So if you look at it on the left, it may make more sense if you look at it here. See how on the left, if you're in the first octant, on the left would be the XZ plane. So on the left is the XZ plane, which is 0. And then on the right is this Y equals 3 plane. So your Y is between 0 and 3. Because on the left is the XZ plane, that's where Y is 0. On the right is the plane Y equals 3, which is obviously where Y is 3. And so your Y is between 0 and 3. So it doesn't have to be between functions. It can just be between constants. It just can't have functions on the outer limit of integration. Okay, so if I'm doing Y first, then my projection is in the XZ plane. So I'm going to look at this. The XZ plane would be this here. So see how it's a fourth of a circle? Why will you not focus? There we go. See how it's a fourth of a circle? So that's, sometimes it helps if you look at it here. I don't know. Here's my XZ plane. See, it's that fourth of a circle right there. The projection is in the XZ plane. So here it is. I've got the fourth of a circle. It's radius 2, because it was x squared plus y squared equals 4. So radius 2. All right, so if I do, and I didn't show the work. I showed the work for this one in the previous group. I don't know what to call it. I showed the work for this one previously. This would be the same idea. So you're solving for x in this case, and you're solving for z in this case, and it works out the same way. You had the plus or minus, but you're in the first octant, so it's only positive. And then the other ones are between 0 and 2. So setting those up, it would look like this. Always check yourself and make sure your outermost integral cannot have variables in the bounds. Okay, it's got to just be constants. But these two, they can have variables or not. It just, whatever your situation dictates is okay. But you cannot have variables on your outer ones. So make sure you always have numbers on your outer ones. And here, because I'm using this to find volume, that's why I have these ones here. You don't actually have to write the one. I just like to write it to reinforce the idea that for a triple integral to be volume, you've got to be integrating 1. All right, now you try this one by yourself. Okay, we're doing z first. So you're going to look at your 3D picture to get the z, and then you're going to do your projection. I'll let you see if you can figure out what plane that's in and draw it, and try it by yourself. So pause the video and try this one by yourself. All right, let's look at the region. So for z goes bottom to top. You always have whatever's smaller at the bottom of your arrow, whatever's bigger at the top of your arrow. So on z's, it would go bottom to top. So you ask yourself, what's in the bottom? Well, in the bottom would be the xy plane, so that's where z is 0. And then when you come up, you're hitting the cylinder. Like imagine you're standing inside. Your feet would be on the xy plane. Your head would be hitting the cylinder. Okay. So you have, for your z, it's between the xy plane, which is 0, and the cylinder, solved for z, which is this. So your projection would be in the xy plane. So if you look at your region here, the xy plane, that's the bottom of this. It's like the floor. So see how it's a rectangle? So the bottom is a rectangle, the back was a rectangle, but the sides weren't. All right, so this one is a rectangle. X is between 0 and 2, y is between 0 and 3. And so your integrals should look like this. Okay, so check your answers, make sure that's what you got. And again, in general, you would not have to do all 6 of them. You're just picking one of the 6 normally. This was just practice setting them up because this is new, so they're kind of working you into these with some of the easier ones. Okay, it also asked you in number 4, I didn't actually read the problem. That would have been helpful. Write 6 different iterated triple integrals for the volume, blah, blah, blah. Evaluate one of them. I forgot when I was making my notes to evaluate one of them. So if you're looking at this on Angel, I put a little note when I post this later. See the last page for number 4 evaluated, because I forgot to evaluate it. So let's flip over and evaluate it. It ended up needing a trig substitution, so I didn't actually show all of the work. I just wanted to kind of get you started. I chose this one to integrate for no particular reason other than it had constants here. But I, in hindsight, might have picked a better one because maybe it didn't need a trig substitution. I don't know. But I was running out of room and time and patience, and so here it is. Okay, so if you're integrating 1 with respect to z, it would be z. And then these are the bounds on the z, so you're plugging it in. So it simplifies down to this. Now you're integrating with respect to y. So this doesn't have any y's on it, so it's like a constant. So integrating with respect to y, you just stick a y on the end. Here's the bounds on the y. Plug that in and you get this. This needs a trig substitution. I couldn't remember exactly where it was in my notes where at work, and I am at home. And so I couldn't refer you to it specifically, but I don't know if you remember that problem that I worked out before, and like all along this side, like I drew a line down the paper, and all along this side, I worked out a trig substitution. This one I think is the very same kind of problem. I think it's the same kind of substitution if I'm remembering correctly. I can't remember exactly what that problem was, but I think it was similar. So you can refer to that on the trig substitution for the work. But anyway, it ends up being this, and then you plug in, so your final answer, 3 pi. So I don't know, maybe some of the other methods would have been, or some of the other integrals would have been easier. I don't know, I just tried that one. Okay, let's look at some other problems now. 7 to 20, all you're doing is evaluating them. They've already set them up for you. You're just evaluating. The triple integrals, evaluating them is basically the same as the double integrals. You've just got to go one more time. So instead of going twice, you got to go 3 times. But other than that, it's the same thing. So you could do you know, I don't know what it would be called if there's double, triple, I don't know what it's beyond that, but let's say you had 10 of them. It's still the same principle. You're just doing them one at a time, and you start from the inside and you work your way out. So always starting from the inside, always working your way out. So you're doing here Z first, then X, then Y. All right, so again, I'm integrating 1. And so integrating 1 with respect to Z is a Z. And then I plug these things in for Z. Be careful with this negative. You've got to distribute it because you're subtracting something that's more than one piece. So just distributing it, putting my like terms together gives me this. Now I'm integrating with respect to X next, because again, you start from the inside and work your way out. Apparently that's on the next page. All right, so integrating with respect to X, let me show you this piece. This piece didn't have any X's in it, so it's just like a constant, just like this. So just like here you stuck an X on the end, here you're sticking an X on the end. So you have this. I have a fingerprint on my screen from where I keep touching it to focus it. There. Okay, integrating with respect to X, now plugging in for X. So I simplify down to here. So that was my middle integral. Now I'm ready for my last integral. This one is with respect to Y. Oh wait, just kidding, I simplified to here. This is the most simplified version. Integrate with respect to Y and plug in, and I end up with -6. So again, we talked about this before, but don't let it bother you that you're getting negative answers for volume, because it's kind of like in Calais when you were doing area, and if it was above the x-axis, the area was positive, but if it was below the x-axis, the area was negative. It's the same kind of principle here. So it's negative because of its location. It's not that you messed up. So don't let that freak you out. Oh, hey, I was going to show you. Check out my, well, I don't know if you can tell. It looks better. My husband pressure sprayed the deck, and so it looks better. He's going to paint it, I don't know. I can't remember what color he said he was going to paint it, but he is going to paint it, so it'll look much better than it does now. So I'll show that to you when it's done, and you can appreciate how much better it looks, in case you saw that on the other video and you were judging me because it looked so horrible before, because it did look so horrible before, because my house is really kind of old. It's like, I don't know, 20 years old or something. So it ages just like I do. So let's try another one. This is number 20. Notice here, instead of Z and X and Y, you have P and Q and R. Same principle, different letters. I remember now what color he's going to paint it. It's a really dark brown, because we have trees that put this black kind of stuff all over everything. I don't know how that happens, but anyway, it's a very dark brown color that he's going to paint it. So it should look much better than it does right now. Okay, so try this one by yourself. This is, again, different letters, but the same principle. So you're working from the inside out, P first, then Q, then R. So pause the video, try this one by yourself. All right, sorry, I got distracted looking at the chipmunk. So it was a longer than normal pause for those of you who don't actually pause the video and try it by yourself. That's what you get. Okay, P first. This does not have any P's in it, so it's a constant, so just stick a P on the end. That sounds weird. Anyway, plugging in, and then you get this. This now with respect to Q, notice you've got a Q here and a Q here. This R plus 1 in the bottom, that's just a constant, so you're just kind of ignoring that. It's like you're dividing it by 2 or something. But that's going to need a U substitution. So you do the U substitution, and you get this. So plugging in, notice the Q's will cancel, but you still have this -2 in the bottom and this. So put that all together, because that's all just a constant, because it doesn't have any of the U's in it. Integrating with respect to U now. Plug back in for U. And then once I've plugged back in for U, I brought my bounds back. So I have these numbers for Q. I plug them in for Q. Simplify. And that must be on the next page. Oh, hold on. In case you were trying it by yourself and you got something wrong, let me give you just a second to look at that so you can pause it here. There's all the work. Okay. Okay, so it simplifies down to this. So for your last integral, you have this. You can do that with the U sub if you need it, but it's a pretty straightforward one, so I didn't show the work. But it's just a natural log. So plugging in, ln of 1 is 0. This was the answer that I had. This was the answer that the book had. So just in case you're looking at some and they do that, remember the laws of logs. So laws of logs, this is 2 cubed. You can bring the power down and then it canceled. So either one of these is totally okay with me. It doesn't matter to me which one you do. All right. Come on, papers. Hold on, sorry. My papers are stuck. There. Okay, got it. Okay, next group of problems. 23 to 36. 23 to 36. Find the volumes of the region. So for triple integrals, finding volume, you're integrating a 1. Okay, remember you're integrating 1. So we're going to look at 24. Here's the picture. I drew it in my notes, but it looks better in the book. So that's it. Here it is. And I've labeled. Okay, I've labeled them. This front one, that's the x plus z equals 1. This side one, that's the y plus 2z equals 2. And so here, just because of the way the functions are, and you really just, you can't, if you're new to this, you can't really just tell from looking sometimes which one's easier. So if you want to just take a minute and play around with some of these, like I originally was going to do dz, dy, dx, but then when I tried to solve this, I had a fraction, I had, the y over 2. And so it's trivial things sometimes, but to keep from having the y over 2, which is a fraction, it was easier to solve it for y than it was to solve it for z. So when I say this way is easier, that again just kind of comes from practice. And so if you're thinking, how did she know that way was easier? Well, because I've been doing this for years and years and years. But you haven't been doing this for years and years and years, so don't expect that it should be obvious to you. That's okay that it's not obvious to you. It just try it one way, and if it doesn't work, or if it's harder, or you end up with fractions, then you just know, try something else. So there's only 6 possible combinations. You'll hit the right one eventually. And they all should work. It's just some are easier than others. Okay, so I am going to do dy, dz, dx. So for doing y first, I look at the 3D picture. So looking at the 3D picture, my y goes left to right. So I say, okay, what's on my left? On my left is the xz plane, which is 0. And as I move to the right, I'm hitting this plane here. So this plane here is on my right. So I need to solve it for y. So I take this, solve it for y, and I get this, and that's my bounds on my y. So now, when you're done with the first one, for the other two, the z and the x, your projection is in the xz plane. So look in the xz plane and see here, this triangle, that's what's in the xz plane. So I drew it here. Okay, this is the triangle, and that line came from, that line, which is here, came from this plane. And so because I'm going to do z first, I'm going to solve that for z. So for z, on the bottom is the x-axis, which is 0. On the top is the line. So set it up this way, and then x's are between 0 and 1. Okay, so this is what it looks like. So you can pause it here now and try integrating it by yourself. All right, so integrating with respect to y first gives me y. I plug in, it gives me this. Notice this would have been like a problem earlier in chapter 14, finding volume by doing a double integral over of a function, a double integral of a function. So this now becomes like what we were doing before. So you can integrate, you should have gotten 2/3. Okay, so if you tried it by yourself and you didn't get 2/3, there's the work. This is a pretty basic one, so hopefully you didn't run across any problems. All right, let's try another one. 26, here again is the picture. Again, I drew it in my notes, but it looks better here. It's a wedge cut out of a cylinder. So you had a cylinder, you only have the left side of it, and then you sliced it off with this, this plane. Okay, so again here, kind of by default, unless it's hard, this is my default one. Again, the reason why I didn't do it this way on the last one was just because I was going to have a y over 2, and I was just trying to avoid fractions. That's the only reason why I didn't do it that way last time. So z first. Z goes bottom to top. So if you're standing in the 3-dimensional thing and you ask yourself what's on the bottom would be the xy plane, which is 0. If you stand up, you would hit your head on this slanted plane here. So the slanted plane came from the z equals negative y. So on the bottom was this, on the top was this, and that would be my bounds on the z. Now I look in my 2D projection in the xy plane. So I've got the xy plane. So xy plane, that would be the bottom. See how it's this half circle? That's what's on the floor there, this half circle. So the half circle, the y's are always negative because they're to the left, and so that's where the y is negative up here. Okay, so that equation came from the unit circle, and because I'm going to do y first, I'm going to solve it for y. And notice here, it's plus or minus, but the y is negative, so you want the negative case. All right, so the y on the bottom is the circle, on the top is the x-axis, and then x is between -1 and 1. So here's the integral. if you want to pause the video and try to integrate this yourself. You can also, hold on real quick, if you want to, you could go from 0 to 2 and double it. That's what the book does sometimes, because this, if you notice, this is the same. If you did just the front half of it, the back half is the same, so you could find just the front half and then double it. The book does that a lot. I don't do that just because I think most people don't think to do that, but it does make it a little bit easier. So if you want to go 2 times the integral from 0 to 1, that would work. Okay, now if you try it by yourself, then come back and check. Here's where you should be first. Then you integrate. Then you plug in, I already integrated. And then you integrate again and plug in again, and then you integrate again. So lots of fractions here, but easy ones. So 2/3 should have been your final answer. I didn't cancel my negatives earlier, so I had all these negatives. That's what all that white out is. All right, this video is getting long. Let's hurry this up. Turn the page. Page 794, we're going to look at average value. Okay, so we're going to look at number 40. Average value of this function over the cube that has sides of length 2. Okay, so I'm in the first octant. My numbers are 2's. It's a cube. So you want to find the volume. I wrote area. Hold on. That's not area. Let's fix that. Volume. Okay, so on a cube, the volume is the side length cubed. And so the side length is 2. 2 cubed is 8. That's the volume. Here's the formula that I'm using for average value now that I have triple integrals. So I wrote area there too. My goodness, what's my problem? That's volume. Okay, 1 over the volume of D. All right, so the volume was 8, so 1 over 8. This is just a cube, so the bounds are all constants. Here's my function. So I'm going to integrate. This one's a pretty straightforward integration. Integrate, plug in, simplify, integrate, plug in, simplify, integrate, plug in, simplify. And so you get 1. So 1 would be the volume here. Not volume, average value. 1 would be the average value. All right. Next, changing the order of integration. 41 to 42. Change the order of integration in an appropriate way. So for whatever reason, the way it's set up maybe is difficult to integrate, and so they want you to swap it around in a way that's easier to integrate. So they didn't tell you which one, but they give you set up one way, and you've got 5 other choices for what's a better way. So this is a good one to kind of practice with what's better. So here, if you look at your function, notice that you've got a y squared up here, and you've got a z here and a z here. So the easiest one is the x. The x is going to be the easiest one to integrate with respect to, instead of having to try to figure out, because on this y one, you'd have to do a u substitution, but you don't have another y here to cancel it, so you can't. And then on the z, you'd have to do integration by parts. So the y is impossible, the z would be integration by parts, the x is going to be super easy. So let's switch it to be x first. All right, so I'm going to change it to x first, then y, then z. So I originally had y was between, did I draw the picture? No. Yeah, I did. Here we go. Okay. So this is the whole thing. It's supposed to just be the first octant. I didn't draw it in the first octant. So, cut it in half and it's just the front part. So pretend like it's just the first octant part of that. Okay, so it was y equals x squared is this, what is it called? Paraboloid? I can't remember. And then y equals 1 is this plane that cuts it off. And then it stops at z equals 1. So it cuts off the top here, and then it stops at z equals 0, so it cuts off the bottom there. So this is the region. But again, only the first octant part of it. It's only the front half. Okay, so this is what it, hold on, let me write. Okay, this is what it is now. This is what I'm going to change it to. Okay, so this is what it is now. I'm going to switch it to this, and that comes from my picture. X goes from back to front, so in the back is the YZ plane. Again, pretend like it's only the first octant of this. I drew the whole thing. In the back is the YZ plane, which is 0. In the front is this shape, so it was y equals x squared, but now it becomes x equals the square root of y, since x is positive. Y is between 0 and 1, and z is between 0 and 1. So that's my order. So here's my integral. I'm going to let you integrate this one by yourself. This one does need a u sub, so try this by yourself, and then when you get done, here's the answer. You can check it. So it needed a U substitution for the second integration. And e to the 0, remember, is 1. Okay. All right, so triple integrals, again, just like double integrals, just one more piece of them, but they're a lot harder to set up. And so when you're setting them up, remember there's the steps in your book. Let's see what page that was. Page 787 to 789. That's all the steps, all that stuff I have highlighted there. But it's basically for the first limit of integration, you're looking at the 3D picture. Then you do the 2D projection for the other two, and then set it up from the 2D projection. So a little bit more complicated, but same principle. So now I get to go eat. I'm excited. I get to go to Shogun for lunch and Buena Vista for supper. So I get all kinds of international food today. So I am hungry, but I'm not going to eat until I go to my restaurant. So I'm off to Shogun and Buena Vista. Don't call me because I didn't give you my phone number. Email me if you have a question.